If you open any science fiction novel, watch any episode of Star Trek, or listen to Neil deGrasse Tyson on a talk show, you will hear one unit of measurement dominate the conversation: the light year. It is poetic. It is intuitive. It connects distance with time. It is the language of the public imagination. But if you walk into the control room of the Hubble Space Telescope, or read the raw data from the Gaia mission, the light year vanishes. It is replaced by something else. Something awkward. The parsec. A unit equal to roughly 3.26 light years. A distance where, statistically, almost no star actually exists. Our nearest neighbor, Proxima Centauri, is 1.3 parsecs away. Sirius is 2.64. The parsec doesn't mark a boundary. It doesn't mark a physical object. It marks a choice. This is not just a story about units conversion. It is the story of a 2,000-year-old impossible math problem. It is the story of a German accountant who became obsessed with the wobble of the Earth. And it is the story of how a decision made in 1838 trapped modern astronomy in a system we can no longer escape. To understand why we use the parsec, we have to go back to when the universe was small. For 2 millennia, the stars were a mystery. The ancient Greeks, like Hipparchus, catalogued them, but they had no concept of depth. To them, the stars were fixed on a crystal sphere, the firmament rotating eternally around the Earth. It made perfect sense. If the Earth moved, the stars should appear to shift. If you close one eye and hold out your finger, then switch eyes, your finger moves against the background. That is parallax. If Earth orbits the Sun, we are viewing the stars from 2 different positions, separated by 300 million kilometers every 6 months. The stars must shift, but they didn't. For thousands of years, no matter how hard astronomers looked, the stars remained frozen in their constellations. This lack of movement was the strongest argument against the idea that Earth orbited the Sun. If Earth moves, where is the parallax? The answer, we now know, is distance. The stars are so unimaginably far away that the shift is microscopic. To see it, you need to measure an angle smaller than a single arcsecond. Imagine a tennis ball. Now, move that tennis ball 1 kilometer away. The width of that ball is 1 arcsecond. Now imagine trying to measure that angle with a telescope made of brass and wood, while the atmosphere boils above you, blurring everything. In 1669, Robert Hooke tried. He failed. In 1728, James Bradley tried. He discovered something else entirely, aberration, but failed to find parallax. In the 1,780 seconds, William Herschel, the man who found Uranus, tried. He failed too. By the 19th century, measuring stellar parallax had become the holy grail of astronomy. It was the impossible barrier, until a man named Friedrich Bessel decided to treat astronomy not as an art, but as an accounting problem. Friedrich Wilhelm Bessel was not born an astronomer. He started as an accountant for a trading company. He didn't just love stars. He loved precision. He loved error analysis. He was the kind of man who would measure the expansion of his telescope tube when the temperature changed by a single degree. In 1837, in Königsberg, Bessel aimed his weapon, the heliometer, a strange telescope with a split lens that allowed him to overlay 2 images and measure the distance between them with terrifying accuracy. His target was a dim, unassuming star called 61 Cygni. Why this star? Because it was fast. 61 Cygni had a high, proper motion. It raced across the sky faster than its neighbors, which suggested it was close. If any star was going to show parallax, it was this one. For 1 year, Bessel observed. But he didn't just look. He fought the noise. He calculated how the atmosphere bent light depending on humidity. He calculated how his heartbeat vibrated the floor. He calculated the wind pressure on the observatory dome. He stripped away every layer of error until only one thing remained. A shift. A tiny wobble of 0.3136 arcseconds. It was the width of a human hair seen from 100 meters away. But it was real. Bessel had done it. He had triangulated the distance to a star. 61 Cygni was 10.3 light-years away. The universe had suddenly acquired depth. The crystal sphere was shattered. But in his success, Bessel and his contemporaries faced a new problem. The math. Measuring stellar parallax had become the holy grail of astronomy. It was the impossible barrier. Until a man named Friedrich Bessel decided to treat astronomy not as an art, but as an accounting problem. When you do parallax trigonometry every day, you get tired of converting huge numbers. You have the Earth-Sun distance, 1 astronomical unit, as the base of your triangle. You have the measured angle in arcseconds. If you simply take 1 and divide it by the angle in arcseconds, you get a distance. Angle of 0.5, distance is 2. Angle of 0.1, distance is 10. It's beautiful. It's simple. It requires no constants, no conversions to kilometers or miles. And so, a new unit was born. The parallax second, the parsec, defined as the distance at which the radius of Earth's orbit subtends an angle of 1 arcsecond. It was a unit of convenience, a shortcut for mental math. But there was a catch. The parsec is based on the number 360, the degrees in a circle, which comes from the Babylonians. It is based on the Earth's orbit, which is specific to our solar system. It is a unit constructed entirely from human history and local geography. It has no universal physical meaning, but for the astronomers, it was the only thing that mattered. It was the width of a human hair seen from 100 meters away, but it was real. Bessel had done it. He had triangulated the distance to a star. 61 Cygni was 10.3 light-years away. The universe had suddenly acquired depth. The crystal sphere was shattered. But in his success, Bessel and his contemporaries faced a new problem. The math. Measuring stellar parallax had become the holy grail of astronomy. It was the impossible barrier. Until a man named Friedrich Bessel decided to treat astronomy not as an art, but as an accounting problem. As the 20th century dawned, a split occurred. Astronomers, building on Bessel's work, marched deeper into the cosmos. They used the parsec because it was the native language of their telescopes. When they looked at galaxies, they used kiloparsecs, thousands, and megaparsecs, millions. But the public? In 1980, when Carl Sagan launched Cosmos, seen by 600 million people, he spoke exclusively in light years. The Andromeda Galaxy is 2.5 million light-years away. It evokes a feeling. It tells you that looking out is looking back in time. It is romantic. The parsec is cold. To say Andromeda is 780 kiloparsecs away feels like a coordinate on a spreadsheet. To say it is 2.5 million light-years feels like a journey. So, we ended up with two universes. The universe of the storyteller, measured in light-years, and the universe of the scientist, measured in parsecs. It was the width of a human hair seen from 100 meters away. But it was real. Bessel had done it. He had triangulated the distance to a star. 61 Cygni was 10.3 light-years away. The universe had suddenly acquired depth. The crystal sphere was shattered. But in his success, Bessel and his contemporaries faced a new problem: the math. Measuring stellar parallax had become the holy grail of astronomy. It was the impossible barrier, until a man named Friedrich Bessel decided to treat astronomy not as an art, but as an accounting problem. You might ask, why not just switch? Why doesn't science just adopt the light year and make it easier for everyone? In 1999, NASA lost the Mars Climate Orbiter. Why? Because one team used imperial units, pound force, and the other used metric, newtons. The spacecraft burned up. $327 million. Incinerated by a unit conversion error. This is the nightmare that keeps astronomers awake. Astronomy is no longer just people looking through eyepieces. It is big data. The Gaia mission has mapped 1.8 billion stars. Its entire database, its entire processing pipeline, millions of lines of code, are built on the Parsec. All the formulas for absolute magnitude, they assume parsecs. The Hubble constant, the expansion rate of the universe, it is measured in kilometers per second per megaparsec. If you tried to switch astronomy to light years today, you wouldn't just need to rewrite textbooks. You would need to rewrite the source code of modern astrophysics. You would risk a Mars Climate Orbiter disaster on a galactic scale. The parsec is not just a unit, it is a load-bearing wall. It was the width of a human hair seen from 100 meters away. But it was real. Bessel had done it. He had triangulated the distance to a star. 61 Cygni was 10.3 light-years away. The universe had suddenly acquired depth. The crystal sphere was shattered. But in his success, Bessel and his contemporaries faced a new problem: the math. Measuring stellar parallax had become the holy grail of astronomy. It was the impossible barrier, until a man named Friedrich Bessel decided to treat astronomy not as an art, but as an accounting problem. So, the parsec stays. In 2012, the International Astronomical Union even redefined the astronomical unit to be an exact number of meters, effectively freezing the parsec as a constant definition. It is here to stay for another century, perhaps longer. There is a strange irony in this. When we look at the deepest fields of the universe, at light that has traveled for billions of years, we are describing it using a unit derived from the distance between a man's two eyes, expanded to the orbit of our small planet, and calculated by a 19th century accountant who just wanted to know exactly where he stood. The universe is vast, inhuman, and indifferent. But the way we measure it? That remains stubbornly, delightfully human. It was the width of a human hair seen from 100 meters away. But it was real. Bessel had done it. He had triangulated the distance to a star. 61 Cygni was 10.3 light-years away. The universe had suddenly acquired depth. The crystal sphere was shattered. But in his success, Bessel and his contemporaries faced a new problem: the math. Measuring stellar parallax had become the holy grail of astronomy. It was the impossible barrier. Until a man named Friedrich Bessel decided to treat astronomy not as an art, but as an accounting problem